Hello, and welcome back to Vincent Statistics, where my name is Vincent Dayap from Chemical Engineering, first year, and section A13. And in this episode, episode 2, we'll discuss Beer-Lambert's law. And this law will be very useful in determining or in solving different spectroscopic questions in spectroscopy or spectrochemical analysis. Therefore, let's first discuss the objectives of this task. The first objective is to answer problems of basic spectroscopy, to comprehend the Beer-Lambert's law, and to understand the theory and usage behind Beer-Lambert's law. So of course, without further ado, let us discuss first the theory behind this topic in the first place. So in chemistry, we have chemical analysis, instrumental analysis, and in this stage, I'm already at the part of instrumental analysis. And I learned that there are some chemicals that can be identified through the usage of light. And how can we identify that element or element concentration through light? Simply put, if you put a sample of an analyte inside the cell, or in this case we call it cuvette, and shine a light through it, as you can see in the left side of the picture, the light is concentrated, or the light has high intensity. Therefore, I name it I0, or the origin, or the original light. And as it passes through something with the analyte or the sample, the light intensity actually decreases. And I name this as the aftermath light, or simply symbol capital I. So what does this mean? This means that when light passes through something and its intensity decreases in its aftermath, there must be something inside the analyte that's absorbing the light intensity from the origin, thereby creating this aftermath light result. So what are these properties inside the analyte that will be able to absorb the light of the origin? So of course, we must take into account the cell pathway, or the distance of the cell from one point to another. And inside the analyte, we must take into account two variables: its concentration and its molar absorptivity, where this molar absorptivity describes the analyte's tendency to absorb light in a certain matter of concentration and intensity of the origin. Therefore, using all of these observations, how would we be able to describe a certain expression or mathematical expression that will be able to relate all in one? Well, let me introduce you to three scientists that had observations that relate to all of these variables. Number one is Pierre Bourgain, and his observation was that light that passes through the atmosphere is diminished. He was an astronomer. He did not have a direct proponency towards this spectroscopic law, but his observation has a very significant contribution towards the law itself. Why? Because his observation helped created this mathematical expression where the rate of change of intensity is directly proportional to the intensity of light from the origin to the aftermath light intensity. And because of this observation, Johann Lambert tried to relate what he observed with Pierre Bourgain's observation as well, where Lambert described that the amount of absorbed light is proportional to the cell pathway, meaning mathematically that the rate of change of the light intensity is directly proportional to the cell pathway represented by L. And lastly, August Beer also tried to contribute something, for he tried to relate the amount of absorbed light in the analyte to the solution concentration inside the cell. Mathematically speaking, the rate of change of light intensity is directly proportional to C. So, the sample concentration. Therefore, how will we be able to combine all three for a great mathematical expression? Well, we have all three observations. When we combine them all, we have this. The change of light intensity with respect to the cell pathway is directly proportional to the light intensity aftermath times the concentration. The negative sign on the left side of the equation represents the decrease rate, or the decreasing rate of change of light intensity. So, how will we be able, this is still not a good mathematical expression. It's still very cloudy. Well, we need to do a few differential equation techniques, integration techniques, for us to further solidify this expression. Alright, so in this expression, we have this proportionality expression, where the decrease rate of change is proportionally constant, proportionally related to intensity times concentration. Since this is proportionality, directly proportional, therefore we can say that the decreased change in rate of I is equal to the proportionality constant times intensity times concentration. Therefore, we can do integration techniques. However, we cannot integrate this as it is. We need to put I on the denominator in the left side and dl on the right side, following the differential equations rule. Looks like all are in order. Therefore, let us integrate. From the left side, let us integrate the change of rate of I from I naught, or the origin of light, to the I aftermath, or capital I. And on the right side, we put the negative sign, and disregard the other negative sign. There was a typo. It's just that the integral from 0 to n negative kc dl. So we would have this expression, the natural log of I minus the natural log of IO equals negative kcl. Following the laws of logarithms, we can say that the natural log of I over IO is equal to negative kcl. When we have this expression, we can further simplify it into our advantage. Why? Let's say we try to put the negative sign of the KCL into the left, and we try to change the natural log into 2.303. What I mean is, we try to change the natural log expression into base log 10 by factoring 2.303 and putting the negative sign on the left side, then putting the 2.303 on the right side through division, and let's try to say that k over 2.303 times CL is equal to negative log of I over IO. Therefore, we can say that this expression, or k over 2.303, let's exchange this to a more easier symbol, which is epsilon. Epsilon times concentration times cell pathway is equal to the negative log of light intensity aftermath over light intensity origin. And this is Beer-Lambert's law. The reason why Burger's contribution is not here is because he was indirectly contributing to this expression. Beer and Lambert actually tried to analyze this method based on the observations of Pierre Bourgaer's atmospheric light conditions. So in short, Pierre Bourgaer demonstrated his observation through the sky, or through astronomy, or through light intensity. However, what Beer and Lambert's were through specifically chemistry. So that's why the law is named after Beer and Lambert, hence naming Beer-Lambert's law. And Beer-Lambert's law describes absorbance. When we say absorbance, I mean that absorbance of the analyte, meaning how much can the analyte absorb the light intensity of the origin. So we have all of these expressions. As you can see on the top left, we have all of these expressions into one equation. Very good. Why? It's because I represents the aftermath light intensity, IO or I naught represents the original light intensity, The C represents the sample concentration. The L represents the cell pathway distance. Epsilon, or let's say E, represents the molar absorptivity, or the coefficient, or this molar absorptivity varies between analytes. Therefore, this molar absorptivity will be different depending on what kind of analyte are you trying to analyze. And lastly, A means absorbance. Now, this means that we can use any equation to find the result of absorbance. It does not matter which you use. It only matters if what can the problem data can give you. Based on the data, it's up to you into which type of equation you will use to get the absorbance. It's just simply algebraic manipulation. And you will see an example in the next slide. So, we'll have the first question for this task. Question number 1. A solution of COH2O 2+ has an absorbance of 0.20 at 530 nm in a 1 cm cell. Epsilon, or the molar absorptivity of this analyte, is known to be 10 liters per mole per centimeter. What is its concentration? So, if we can further understand this, let us draw a diagram as shown in the picture in front. So, and let's assign our variables. So we have the let's manipulate Beer-Lambert's law and let us assign our variables. So we're not given a concentration because that's what we're trying to find, but we have an absorbance which is 0.20. We have a molar absorptivity which is 10 liters per mole per centimeter, and we have a cell pathway, or the distance of the cell, which is 1 centimeter. If we try to remember how we computed Beer-Lambert's law, we have epsilon, we have A, we have L, but we don't have C. We don't have I and we don't have IO. That means we don't need to use the negative log I over IO part of the equation. Since A is equal to epsilon CL, then we can just use this part of the equation. A equals epsilon CL. And we have A, we have L, we have epsilon, we don't have C. So simple algebra, let's isolate C. Using division, we will get C equals A over epsilon times L, or the absorbance over molar absorptivity times the cell pathway. Let's try to use this equation in action. So, we have the solution, we have the formula. Let's substitute the variables. We have C, or the concentration, equals the absorbance 0.20 over 10 liters per mole per centimeter times 1 centimeter. As you can see, the centimeters in the denominator can cancel out since the centimeter in the pathway, or L, is 1 centimeter and the centimeter in the epsilon has the -1 expression. In mathematical sense, when you have an expression that's going to -1, we can just say that it's 1 over that variable. And a variable that has similar numerator and denominator can cancel each other out, thereby leaving us with liters and liter per mole. But since there are in the denominator, reciprocally speaking, we will just need to transfer the mole part into the numerator, thereby having a result of 0.020 mole per liter. And remember, in chemistry, mole per liter is actually a unit of molarity. And it makes sense, since molarity is a unit of concentration. Thereby, this final expression, or this final answer from this problem, is 0.02 molarity, or molars. To further formalize the final answer, the concentration of the COH2O2+ sample is 0.02 molars. Let's have the next question. The absorbance of an unknown MnO4 negative solution is 0.5 at 525 nm. When measured under identical conditions, a 1 times 10 to the negative 4 molars MnO4 negative is found to have an absorbance of 0.2. What is the concentration of the unknown? We're given a hint on how to solve this problem. We need to use ratio and proportion. So, how can we solve this? So first, we need to manipulate Beer-Lambert's law, and we need to know that the relationship between absorbance and concentration. So, let us assign our variables. We were given an absorbance of 0.5, a concentration of 1 times 10 to the negative 4, and the absorbance of that concentration is 0.2. We are not given the concentration that gave the absorbance of 0.5. So, as I said again, we do not have I over IO, but we do have C and A. So we can just use ECL or epsilon CL equals A. We need to find the relationship between A and C, or the absorbance and the concentration. Therefore, we can say that epsilon times cell pathway equals absorbance over concentration. That means that this is the relationship based on Beer-Lambert's law. Since we're given another concentration and another absorbance, we can assume, and since they're using the same analyte, that means the molar absorptivity is the same. And since they're using, let's say, the same machine to measure this, and when we say it's the same machine, that means they're also using the same cell, which means that L is constant between the two changes. Therefore, we can say that at first measurement, A1 over C1 when C1 is unknown. That's what we're trying to find. And at the second case, that's the first case. The second case, in blue, is A2 over C2 when C2 equals 1 times 10 to the negative 4 molars. So, if E and L are the same, we can just say that A1 over C1 equals A2 over C2. So we just combine the two cases, the two case expressions, ratio, thereby creating a ratio and proportion expression. Since we want to find the first concentration that gave an absorbance of 0.5, it's simply algebraic manipulation, where we cross-multiply both of them, and we divide A2 so that C1 will be isolated, giving us the formula C2A1 over A2 equals the first concentration. And this is the formula that we will use in order to determine the first concentration that gave an absorbance of 0.5. So let's see this equation in action. So C1 equals C2 times A1 over A2. C1 equals, as given by the variables, C2, or the second concentration, is 1 times 10 to the negative 4 molarities, or molars, times the first absorbance given, 0.5, over the second absorbance given, 0.2. Therefore, our concentration is 2.5 times 10 to the negative 4 molars. And it makes sense because molars is a unit of concentration. Let's formalize this final answer by saying that the concentration of the unknown MnO4 sample is 2.5 times 10 to the negative 4 molars. So let's go back to our objectives. Our first objective is to answer problems of basic spectroscopy, and we've done that with flying colors. The second objective is to comprehend Beer-Lambert's law, and we try to find the formula for Beer-Lambert's law, we try to know its proponents, and we try to know how its process in getting that formula came to be. So we did that with flying colors as well. Lastly, we understood the theory behind Beer-Lambert's law on cell pathway, light intensity, origin and aftermath, molar absorptivity, concentration. In short, to understand the theory behind it, we need to relate everything that we know in one mathematical expression. Because remember, in science, it's just merely saying words in English or in whatever native language you use and try to express them in mathematics. Because mathematics, regardless of what origin of nation you came from, will help us understand the problem fluently. Therefore, this is where we end for episode 2 of Business Statistics. My name is Dayap Vincent M, first year chemical engineering student from section A13. Again, episode 2, Beer-Lambert's Law, and I would like to thank you for listening to this task.